All right, so in this pre-lecture, we're going to talk about aerobic and anaerobic treatment at a very, very high level. So we're using aerobic and anaerobic treatment in different components within wastewater treatment. We've already talked about some of these components like activated sludge, but we haven't talked specifically about the fact that there are different mechanisms. So this lecture is really meant to kind of give you the general principles that are governing these two different types of reactions. And they're going to be used in multiple different treatment units that we talk about. So aerobic and anaerobic treatment or digestion, whichever one you want to call it, they are both governed by microorganisms. So this is a biological type of treatment. Everything we've talked about so far in class has pretty much been physical or chemical treatment. So physical treatment would be things like sedimentation, chemical treatment with things like coagulation or chemical dosing for disinfection. Aerobic and anaerobic treatment is biological in nature. So you have living organisms in the system and you don't want to kill them. So there's two types of digestion that we can use. We can use anaerobic digestion or aerobic digestion. So if it's been a while for biology, just focus on the fact that anaerobic digestion is the oxidation of organic materials by microorganisms that don't need oxygen. So it's the first reaction. So they're going to take organic material, they're going to take oxygen that's in other sources, so things like other compounds, but not oxygen itself as we think of it as O2. So we're not using oxygen in the form of O2. And those anaerobic microbes generate new cells, energy for their cells, methane gas, CH4, CO2, carbon dioxide, and other end products. So these are organisms that don't need oxygen to produce energy and reproduce. So anaerobic means without oxygen. In contrast, your aerobic digestion is biological oxidation with oxygen. So these organisms must have O2 in the system in order to move forward, make new cells, reproduce, and produce energy. So the key difference is oxygen. So if it helps you to remember, the root of that word, A-E-R-O, arrow, means oxygen. A-N in front of that arrow means without. So if it helps you remember, A-N is without, and A-E-R-O, that root, is oxygen. So if that helps you, that's a good way to think about it. So that's the key difference between the two. You either have oxygen or you don't. The microorganisms that you use in both of these treatment processes are going to be different as well. So keep that in mind, that they're not the same organisms that are going to do these processes. So the purpose of these two different types of treatment is really the breakdown of organics. So wastewater has heavy, heavy organic loads, right? We have food coming in from dishwashers. We have restaurants that are washing food down the sink. We have feces, urine, it all has high BOD content, high organic content. And that's something that we don't want to be dumping into our receiving waters. So we make what are called bioreactors, and bioreactors use either anaerobic or aerobic treatment to break down the organics. So the type of organics we have and the type of organics we need to break down are going to depend on the microorganism is going to depend, that we choose is going to depend on what type of organics we're trying to break down. And then that type of microbe is going to tell us whether we need oxygen or not. So we look at the organics in our system and we say, who can break down those organics? And then based on who can break down those organics, do they need oxygen or not? That's basically what the idea is when we're designing these processes. So it's going to help us to remove not only organics, but volatile organics. We don't want organics that are going to cause issues in our receiving waters. And it's going to decrease BOD concentration. So prior to this pre-lecture, we've talked about treatment that pretty much only goes after TSS. The other big one, remember, in wastewater treatment is BOD. So these types of treatment are going after that BOD component, and that's really important. So here's a quick comparison of the two. So aerobic uses oxygen, anaerobic doesn't use oxygen. That's the baseline comparison to make between the two. Aerobic is going to produce water as a byproduct. Anaerobic is going to produce methane gas as a byproduct. Methane gas can be used to power what we call biogas digesters. which is just another different technology that we're not going to really talk about in this class, but it can be used to make energy. So anaerobic treatment can be used occasionally as an energy generation tool, which is kind of interesting from a sustainability standpoint. But they do have lots of things in common, right? So they use organics as their substrate for the microorganisms. So organics are the food for the microorganisms. Now there's different types of food, and that's going to help us choose whether it's aerobic or anaerobic. CO2 is produced as a byproduct in both of these cases. Both of these microbes are going to follow the growth curves that we've been starting to talk about in class. So we're a little bit behind in class in terms of getting to this, but we're going to talk about how microorganisms grow, and they both grow the same way. And they follow the Michaelis-Menten equation that we talk about in class when we talk about activated sludge and substrate and that kind of concepts. And we also use heterotrophic microorganisms in wastewater treatment. So they get their food source from organic or inorganic compounds. They're not doing photosynthesis. Photosynthesis would be done by autotrophs using light. So this is kind of a comparison, a couple different tables that I was able to find online just to give you a sense of, when do we use these and when do we not use these? And so one of the things that's different between aerobic and anaerobic is the space that these types of bioreactors can take up. So anaerobic systems are generally smaller, and aerobic systems are generally larger, so that's important. But aerobic systems can help us remove nutrients. They're very good at using nitrogen and phosphorus, whereas anaerobic microorganisms really don't do that. So if we want the benefit of nutrient removal, that's one of the things that we'd care about when maybe potentially choosing between these types of organisms. The capital investment costs for anaerobic tend to be a lot higher, but their maintenance costs over time tend to be a lot lower. And the converse is true when it comes to aerobic. It's pretty easy to put this thing in place, but it's very difficult long-term to pay for operational costs. So that's important, especially when you think about small systems. And then these other tables, what I recommend you do is just take a second to pause the video and just kind of look through these. These are talking specifically about the bioreactor themselves, and we're going to talk about bioreactors in class, not necessarily cellular respiration. But you can see how they're kind of used for different ways in treatment. So pause the slide to just kind of give yourself a second to digest what's in these tables. So I like to always have some pictures because it kind of helps us. What you'll see in the bottom is an example of some bioreactor aeration basins. So you can see kind of the air coming up in the system. That's what that white kind of foam is on the top. So these basins can be open to the atmosphere. Many times there's an aeration phase. And what you'll see on the top left is just two different ways of operating bioreactors that use anaerobic and aerobic principles. So you have kind of an aeration chamber like we've been talking about with activated sludge, and then you have some kind of a physical process afterwards to remove solids in the system. And these processes can be either aerobic or anaerobic depending on what you're trying to remove from the system. So you can have the same process flow diagram, but have different processes happening inside them in terms of biochemistry. So I put this slide in here as just kind of a refresher of biology. If you never took biology or if it's been a long time since you have, these are the two different cellular pathways by which aerobic and anaerobic respiration occurs. So the idea is in aerobic respiration, we take oxygen and we take our organics and we run through these different steps of glycolysis, the Krebs cycle, all of these different processes, and we're producing ATP, which is energy. We're also producing CO2 and we're producing water, and we need oxygen in order to do so. In the anaerobic respiration, which is on the right side of the screen, we don't need any oxygen to go through glycolysis and the pyruvate cycle, so we're creating different byproducts on the side. And all I really want you to take away from this slide is that there are different biological processes that are happening, and there's different byproducts as a result of those two. And so we want to just be aware of what byproducts we're going to make, because that's going to be important with how we potentially can recycle these organisms in maybe an activated sludge process, or how we're going to have to remove them in the system. All right, so some key parameters you're going to need to know for design purposes. We're going to need to know the characteristics of the organics in the influent wastewater. So we need to know what types of organics we have so we can make a decision between aerobic or anaerobic microbes to break down those substances. And a lot of that's going to be based on BOD content, taking a look at what's in the BOD and whether or not we have volatile, suspended solids, that kind of thing. We also need to know whether or not aeration needs to be a step in our system. So remember that aerobic microorganisms are going to need that constant source of oxygen. So if they need that source of oxygen, we may have to have that aeration step. Remember that microorganisms are going to be influenced by temperature and pH. We don't want to kill these microorganisms. It's different from disinfection. Disinfection, we try and kill things. Here we want to keep them alive. And they like to live in a very specific temperature and a pH, just like humans do, right? There's a temperature that we kind of prefer to live in, right? And so being aware of those is going to be important. And then to maintain that temperature, we might actually have to apply heat. So you can think maybe if we put one of these systems in a place that has very cold winters, you're going to have to keep the heat levels relatively constant in the system. And so that's kind of an important thing as well. In class, we're going to talk about some key calculations. So things like solids reduction rate, digestion time, organic solids loading, sludge feed concentrations, recycle ratios. All of these calculations are going to be important to designing these types of bioreactors. So I've been throwing around the term bioreactor, and it kind of makes sense to have a slide to just talk about it very quickly. Bioreactors are treatment steps where you're using one or the other, maybe both, aerobic or anaerobic treatment. So using activated sludge, using aeration and a sedimentation, that's an example of kind of a bioreactor process. So bioreactor just refers to when we kind of have tanks that have biological systems in them that are working and doing things in the system. So basically what's happening in a bioreactor kind of process flow diagram is that we have a biological removal, which is normally somewhere in secondary treatment, and it's paired with a physical process. So something like settling or membrane filtration to try and remove solids and organics from the system. So bioreactors have lots of different configuration, but overall the principles that they're going to use aerobic and anaerobic digestion in them. So in class, we're going to talk about some of the principles that you need to solve for things like solids loading rate, how do you design these things, and what are the different types of designs. And then we'll talk more in depth about bioreactor design specifically.